Okay, so in Lab 7 what we're doing is we're actually looking at the two separate programs. We're going to use the pulse width modulated template and the timer input template. And we're doing basically two different things. The first part, you'll see the pulse width modulated wave, and what you're trying to sort of do with this is you're looking at the code and you're seeing, okay, remember with a pulse width modulated wave, you can have, using a single timer, you have, for example, here CCR1, CCR2, and CCR3 that you can use to change. And so while you have one timer, you can have multiple square waves with different duty cycles. So that's essentially what's going on here. And we've talked a good bit about the pulse width modulated wave. So I don't think really any extra time needs to be spent there, except you will see the demo in the lab portion of it. The nice thing about this, though, is the last thing it's telling you to do here is it tells you to attach RGB LED. So when you attach that, you'll see a bunch of these pins there. Jitendra will help you figure out how to attach the LED. And you can see what you're doing is basically you're changing the red part, the green part, or the blue part. You're assigning a different CCR for each one of those inputs to basically develop a different color that showcases at the output. Okay, so check out what's going on there. And then the next part is using the timer input template. And so the first thing it says is, what are these things doing here for those two registers? And it says, run the code and apply an input signal from the signal generator to pin A0. What does the number recorded represent? So that's going to pop up on the LCD. And then it just says modify to show frequency instead. So let's look and see what's going on just in general by looking at another example that's in the book. Okay, this example is in the book and it talks about measuring the pulse width. So what they're doing here is trying to see what the time is for that particular pulse. That's not what's going on in your code in the lab actually, but it's sort of similar. So one of the things that you can look at that's going on here is they're actually assuming the input polarity is low at the input. And so then what they're trying to do is do this with interrupts. Now remember, we're not doing it with interrupts, but we can still get the basic idea here. So what's happening is first it's coming in here, and this if statement is looking at this input flag and comparing it with, the status register for the timer 4. And remember, this is one of those startup constants, and so it's basically saying if that interrupt flag is set, then go into this if statement. So basically, if the interrupt request has been happened, we're going here, and it says current captured is whatever is left on the CCR. And so then remember, this is key for the next part. When we read here, we're actually going to reset the interrupt flag. And then it says signal polarity signal polarity equals 1 minus signal polarity. So if the signal polarity is 0, then signal polarity would switch to 1. And then, if this gets in this if statement again, which would be like over here, signal polarity would be 1 minus 1, and it'd go to 0. So basically, this is sort of like toggling signal polarity there. That's all we're really doing with that statement. And then it says here, if signal polarity was equal to 0, well, what does that mean? If you've done 1, and then you've come back here, that means you're here, and it says pulse width equals current captured minus last captured, and that's within this statement, but also within the whole if is this last captured right there. So basically what that's saying is, okay, we've been within this if statement, and then we've captured again, So we have the current capture is going to be this value. The last captured after this has been done is going to be this value. So we can get the pulse width from saying current captured minus the last captured, and we'll get that pulse width right there. Then the rest of this stuff is just talking about checking if overflow has occurred and so forth. And it's not something that we really have to worry about as long as our timer and clock settings are such that we don't expect overflow to have occurred. Obviously, this code is set up for that. Now, what we're doing in our lab is something similar but a little bit different. We're doing, as you'll find out, a calculation of the period of a square wave. And how we're doing that is, okay, we should know what is going on with these motor registers right there. That's setting up the timer appropriately. And how it's doing that is it's setting up the pins that we're using, which obviously better be pin A0. So notice these are all in the lower order. That's like 1, 1, and those last 2 bits of that motor register. And then here we're putting in 2. So we're doing things with the last 2 bits there, and then we're setting up the alternate function register. So that must be tying it to a timer. Then we're enabling the timer here. Here you can see we're using the timer's prescale of 15. So we're taking the timer clock and dividing it by 16, so that slows the overall timer clock down. Then we see EGR and CCMR1 and CCER, and let's just talk about those things a little bit. The EGR, if you go look, again, this, they have a bit code representation you can do for this, but this is trying to make you look and see. So if you go look, for that bit, when that bit is set to 1, it's basically is a reinitialization phase. So reinitializes the counter. And it generates an update of the registers. And so that's what's going on there. So basically we're reinitializing the counter and saying, okay, let's go. Now, what do these 2 lines do? This is what it specifically asks you in the code. And now, while it looks like just 1 bit is doing something, there is more than that. But one of the things that you should be able to see here and verify is that it, input capture 1 gets mapped to timer input, TI1. And CC1 is input. So that's what's going on there. And then especially here, it's not just 1 bit, it's 3 bits that you have to look at for CCER. And it tells you, the type of input things that you're looking at. And it says, okay, the 1 here is enabling the capture. And then it's not the next bit. Well, excuse me, it is the next bit. It's this bit. Let me erase this here to make sure it's clear. The next thing you have to look at is this bit, skip a bit, and this bit. And verify that that's the case. Go look at what is going on with the CCER register and make sure you see. And that says we are capturing rising edges. So and so that's what's going on with those 2 bits. Then you see it sets 2 time values. So basically this is similar to this last captured and current captured from the previous slide. Okay. So when we look at that, we can see, okay, what's happening? Okay, here it says while 1, so that's just doing this while loop forever. Here we're looking at time 1 equals the input CCR1. Well, when's that going to be set? That's going to be set when we get a rising edge, right? That's going to be when it's clocked, and then it's going to reset it. And then it says here, oh, well, while that timer value is time 1, so it's going to, until we see another edge, another rising edge, it's going to sit there and still have the CCR1 register of that timer still be time 1. So while it's still doing that, it stays within that while loop. But once we get another rising edge, we exit the while loop and we come here and we say, oh, time 2 equals time 2, the timer's CCR1 again. Okay, so now what we've basically done is if we have a nice square wave coming in, of course it doesn't have to be a square wave coming in, but if we're reading rising edges, one of them is going to be this one. That's going to be basically time 1. And then now it's not reading falling edges, so it's not going to trigger there. It's going to trigger over here. So that's time 2. And so this gives you time 2 minus time 1 will give us the value of the period of that wave. Obviously you could change this up and you can get falling edges, and if it was periodic with a 50% duty cycle, you could measure this and double it and get the period or whatnot. So this is basically just a simple program that's telling you how to get the period. It's a little bit different, but remember, we don't have to use all the flags because each time you read the CCR value, it's going to reset that flag that we need to reset. So we don't have to do any of that and go through interrupts. But the disadvantage of our method of doing it is what? We're sitting in here in this while loop waiting forever until it happens. So that's that's the polling technique, which is terribly wasteful on CPU resources, but it does work. So anyways, that's all we need from this, and the next videos, parts of this video will be Jitendra demoing what's going on in the lab.
And so for this week's lab, part 1, you'll be using 3 ports as output. So the ports will be PH0, 1 and 2, which you will connect with the probe to the oscilloscope. Now if you go to your lab worksheet, you'll find out that the first job for you is to find out the frequency of your PWM wave, and here I have written the formula, which is to find the period, and after you get the period you can find the frequency of it, and the ARR value is the decimal value you can get from the template code. And your second job is to assign the value of ARR to make the frequency 500 Hz, and then you get the setup of those 3 ports as I've said before. And after we run the code, we'll get something like this. So if you look here, you can see I've given the output from the port 1 to the channel 1, and the output of the port 2 to the channel 2, and the output of the port 0 to the channel 3. And if you look at the waves, you can find out that the output of the wave on the P1 port have the duty cycle of 50%, and for port 2 have the duty cycle of 100%, and for 3 is 0. And if you look at your code on the I guess is a timer CCR registers, you will understand why you are getting this. So after you calculate the frequency of your PWM wave, you can make sure that you calculated it correctly by using the oscilloscope. So In order to find out the frequency of your wave using the oscilloscope, you can use the measure button here and you press the add measurement, go to the source. So for now I'm using the source 1, and then go to measurement type. Here are like snapshot, period, frequency, you have the duty cycle as well, but for now we will use just the period and do OK. Then if you go back, you can see that the frequency that I get here is 500 Hertz. So I already calculate the value for the ARA value to get the 500 Hertz frequency. So if you calculated that correctly, you will have the same frequency on the oscilloscope as well. So after you finish the oscilloscope part, now the next part is your RGB LED. So you plug the pins 0, 1 and 2 to the RGB LED, and here is your RGB LED pin configuration. You can look at it online or whatsoever. Just you need to remember that the longest pin here is a ground pin. Now we will hook that on our board and see what happens when you compile the code. So here I hooked the LED on my board. Just you have to make sure that you put the resistor in between the pins and your output pins and your pins of the RGB LED. Now after I ran it and load it, you should get something like this. So that should be what you'll be getting at the end. So this will be the setup for this week lab part 2. So here you can see you have to give an input to pin A0 from the function generator and look at the LCD display. So after you compile the code and load it, you could see that I'm getting a time period of the given input. So it's in microseconds, so you can see here I have about 1000 microsecond of period because I'm giving 1 kilohertz of the frequency. So your goal will be for this lab is to figure out what should you do in the code so that it will display the frequency.